Waterfowl hunting is a common activity across the country. It typically entails a hunter heading into a marsh or swamp using a boat or waders to attempt to trick ducks and geese into coming into a shooting range to be harvested. The Waterfowl Retrieving System team has been tasked with upgrading the dog replacement given to us by the previous year's team to eliminate the risk posed to dogs when hunting in close proximity to alligators and snakes. The robot in question, the Fowl Fetcher, is an innovative design and will be capable of traversing multiple terrains in the case that a bird is downed on land or in the water. It will also have some autonomous systems, such as an automatic return function and the ability to mark a bird on the controller screen using the integrated camera technology communicated from the robot back to the controller.
After receiving the robot from last year's team, we realized that the pontoon design, motor controller, and wireless controller all needed to be upgraded. After researching different drive system designs to match the previous screw design on the robot, we decided via our decision matrix that alternating rubber pieces at an angle on the pontoon would add the much-needed shock absorption and rigidity the robot needed to drive more efficiently on all terrains. The updated motor controller needed to have the ability to be coded to operate the drive system motors or have the code built in to be able to handle similar to the tank's drive system, as well as handle the current draw from the two motors. We chose the Sabertooth 2X60 as our upgraded motor controller since it has air-cooled functionality and is able to withstand our constraints on the drive system. After hardwiring in the two motors for the drive system into the new motor controller, the current draw is now not exceeding the current limit and the robot has the same drive style as the tank.
The operator of the Fowl Fetcher will use a single joystick on the new wireless controller to navigate the robot out to the downed duck utilizing the robot's live camera feed displayed on the old controller. Once they have the duck in sight within the feed, they are able to place the target on the duck on the old controller's display. After the duck is secured within the robot, the operator will flip a switch on the controller signaling for a return. This return will be implemented using waypoint-based GPS navigation algorithms, which will autonomously retrace its steps stored in the GPS breadcrumbs it left on the path to the duck. Heat sensor code will also be implemented and is ready to be put into the drive system code to watch the heat levels within the electronics box.
This senior design project has proven to be a difficult task due to the innovation that is required, as well as the lack of resources to compare it to. The given product proved its functionality and set up a future for this platform to continue to grow into a commercially produced product. All systems are prepared to be implemented into a real-world environment. The drive system has been proven effective in water and on land, as has been tested in both cases. The arm assembly can effectively be operated remotely to pick up objects and place them onto the robot. There is also a vision system that is capable of tracking an object, and in this case, a duck decoy was tracked. This will allow the user to track the downed bird as they retrieve it. Overall, the effectiveness of this innovative new robot design has been demonstrated and is ready for Phase 2.
In the future, it is recommended that the robot be downsized if possible to limit the overall weight. Scaling down the size of the robot would also allow for smaller components and a decreased price, allowing for the possibility of manufacturing and selling them as a commercial product. Implementation of the GPS return system through motor controls and adding the depth camera image recognition to the system would allow for the completion of the autonomous portion of the project. With regards to the vision system, someone with knowledge in machine learning should be able to apply transfer learning to our problem and reduce computation costs enough that it can be implemented on the robot. Since there are two controllers needed to fully operate the robot, integrating the screen into the upgraded wireless controller will overall help the user operate the robot as a whole. Implementing the heat sensor code into the drive system code as it stands will also help keep track of the temperature inside the robot and help reduce overheating within the electronics box.